also we were cooled down, and then the problem was solved. So that is his character. His qualifications are here. And the title of his talk is quite suggestive, Marriage of. So I'm curious to know who is the husband and who will be the wife here. So let us wait and let us see. Nowadays, I suppose it doesn't matter. But both can be husbands or both can be wives also nowadays. So let us see. It's as if we are invited for a wedding, and at the end of the talk, the wedding will take place. So let us see.
Okay.
Slide right.
Go up, then down. Okay. Can you hear me? Yes, thank you, Professor Joshi. See, in all staff meetings in the institute, in the department, at the end, I will make some statement. So my colleagues used to say, Vittal Rao will always have the last word. And today also, I am going to have the last word because I have the last talk. Okay. Well, usually in a marriage, there'll be a good feast, lunch. So we already have the lunch. We have a reverse now. First the lunch and then the marriage. Okay. This is a highly non-technical talk. Some random thoughts that I will throw open. I think it was Hardy who said, young men should prove theorems, old men should write books. Of course, as a young man, I never proved any good theorems. As an old man, I never wrote any books. Okay. But Hardy said also, it is difficult for old men to talk mathematics, but they can talk about mathematics. So as an old man, I'm going to talk about mathematics and not talk mathematics. Okay, so this is a very light talk, completely random. So in keeping in tune with all the random processes that the engineers do these days. So first of all, I will start with an anecdote. Okay. You see two people there on the screen. How many of you can recognize them? That's Feynman. One on the right side, the banjo gives him off. He's a joker. He was a kind of a joker who would always play the banjo. If you had seen the movie Oppenheimer, in that also you will see the person who is playing the character of Feynman will be playing the banjo. Okay. Who is that other person on the left? Perhaps not many of you, some of you might not have known. That's a famous writer, American fiction writer called Herman Oak. Okay, he lived for 104 years, and even at the age of 95, he wrote a book. Okay, and of course, that is Richard Feynman. Now, what is he's a physicist, he's an author. What does mathematics and engineering got to do with this? Okay. Okay. Well, I'll show you some of the books that Herman Oak wrote, just for sample. There's a book called The Winds of War. This was made into a television mini-series, and I happened to be in the US at that time. I saw this series, a very wonderful series. And then another book, War and Remembrance. You will see that war coming in. War was his favorite topic. War and its effects, or science and religion. These were his two favorite themes in writing. And here is another book he wrote, The Caine Mutiny. Some of you who belong, hardly anybody is there in the audience, who belong to my age group. There was a movie, Hollywood movie, The Caine Mutiny, made in 1954 with Humphrey Bogart as the lead role. Okay. Now, Hermann Wouk, his favorite topic for writing books. Of course, before I continue, I request Professor Joshi to warn me 10 minutes before the talk ends, because otherwise I will go on. Okay. He wanted to write a book on the Second World War, because his favorite topic was the war. So one of his friends, when he was discussing this with one of his friend told him, if you are going to write a book on Second World War, there better be a chapter on the atomic bomb and the Manhattan Project. And he says, who do I talk to get more information about this? Then his friend suggested, you go and meet Richard Feynman. He, as a young scientist, had worked at the Manhattan Project, and is a very interesting character also. So you should go and meet him. So Hermann Wouk went to California, Caltech, to meet Richard Feynman. And they two had a very long discussion. Obviously so, because the two had a lot in common. Both were from New York, both were Jews, both had been recruited for work in the Second World War. Feynman in the atomic bomb project, and Hermann Wouk was a reserve Navy officer. But they had one thing which is not common. Hermann Wouk was a very devout Jew. Richard Feynman was pretty much an atheist. So they had a lot of things to discuss about, in addition to atomic bomb and the Manhattan Project in the Second World War. So they got along well. They talked nicely to each other. And when Hermann Wouk was about to leave, just at the door, Feynman told him, Hermann, one question. And then he said, what? Do you know calculus? He said, what? Calculus? He said, no, I don't know calculus. Then Feynman said, you better learn calculus, because that is the language God talks. Okay. Several years later, Hermann Wouk wrote a book at the age of 95, and he titled the book as The Language God Talks. And he mentions in the introduction about this meeting with Feynman. Now, okay, there was a lot of interpretations as to why Feynman said this to Wouk, learn calculus. There are in the blogs and some articles, etc., you will find several arguments on this. One of the arguments is that as an atheist, Feynman wanted to score a point over Wouk and tell him that it is not the language of the scriptures that the God speaks, but it is the language of mathematics that God speaks. And the others, more probably balanced, rational people, feel that the reason why Feynman might have told us was that was a period when mathematics had done so much to physics. They were all fascinated and enamored about mathematics and its role in physics. Okay. So that's probably the admiration for what mathematics had done to physics. Particularly, for instance, most of them were fascinated by the way the Maxwell's equation really revolutionized the theoretical and mathematical physics. And he has put together several experimentalist ideas and added his own insights, and finally was born electromagnetism. Okay. And these equations, at least one can say they felt that mathematics is the language that, or most importantly calculus at that time, is the language that of God, science speaks, rather than the language of God speaks. Okay. For example, Ian Stewart says Maxwell's equation didn't just change the world, they opened up a new one. Such a fascination was Maxwell's equation and the role math played for it. And Ulam is even further admiration that just a few scribbles in the paper or a blackboard can change this world. That's the power of mathematics. Okay. They were even had a T-shirt. Okay. God said Maxwell's equation, and then there was light as an electromagnetic wave. Okay. So there's such a fascination for the role that mathematics played. So the same ideas, the same sentiments were expressed by the way, Eugene Wigner got the Nobel Prize in 1963 and Richard Feynman got the Nobel Prize in 1965. Okay. And the sentiments were expressed by Eugene Wigner in what was known as the title called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It's a very fascinating lecture and very wonderful article. It's very easy to find. In fact, if you Google unreasonable, 0.9999 probability, the first thing that will appear is this. Okay. And it's easily available at a PDF version, one can see. And what Wigner brings out in this article is how several ideas of mathematics developed in a completely different context, which has nothing to do with physics, several years later come out as the right tool to answer the right questions in physics. For example, Riemannian geometry. And it was more from the point of a geometry and non-Euclidean geometries in the parallel postulate that it all started. But eventually that's what Einstein needed for general relativity. That sort of surprise element is what he calls as unreasonable. It's just a grudging admiration for mathematics. It's effective, it's very good, but it's very unreasonable. He didn't even think of this problem when he did it. But exactly it's going to solve my problem several years later. Okay. Now, in response to, and as I said, that article is available freely in the internet. One can download and read it. In response to Wigner's talk, Gelfand Wigner wrote a famous article. Of course, he wrote about physics. Whenever he said natural sciences, all he wrote was about physics. Okay, but there is only one thing which is more unreasonable than the unreasonable effectiveness of mathematics, and that is the unreasonable ineffectiveness of mathematics in biology. So many in my generation and previous, if you are not good in maths, you do biology. If you are not good in biology, you do maths. This was the sort of thing. They never met. Okay, so that's what Gelfand felt. Of course, as a digression, in response to, again, this maybe if you search a little bit hard, you will find this article. But in response to Gelfand, the computer scientist Adelman of the Richard Shiver Adelman cryptography fame, Adelman wrote, well, that's not true anymore. Mathematics appears even in biology. Okay, so that is settled. So the unreasonable effectiveness of mathematics is not only in physics, but is not only in the physics, it's also in biology. And therefore, at that time, the effect of mathematics was highly fascinating to physicists and natural scientists. 10 years after Wigner gave that article, roughly, Wigner was about 1959, and this is about this article was about 1960. 59 and 70. Article 69. Freeman Dyson wrote this article, and it came in the bulletins of the American Math Society. And these also physicists. The title of the article was Missed Opportunities. Okay. He calls it the missed opportunities because essentially Dyson's argument was that many things that physicists could have discovered earlier did not happen. They missed that opportunity to discover earlier because still the physicists were not communicating with the mathematicians properly. He gives several instances in that article. And more importantly, he even gives instances where the mathematician Dyson was not talking to the physicist Dyson. Otherwise, he said, I could have myself found out a few things. When I was doing mathematics, I was doing mathematics. When I was doing physics, I was doing physics. I didn't connect the two. But more importantly, in that article, in the introduction, he writes, as a working physicist, I am acutely aware of the fact that the marriage between mathematics and the physical sciences, natural sciences, which was so enormously fruitful in past centuries, has ended in a divorce. No wonder this fellow said he will talk about marriage. He's already in divorce. Okay. And that's amazing. Okay. And he says, one of his friends said, whenever such a divorce takes place, one party loses heavily. Now in this, whether physics lost or math lost. And Dyson very cleverly doesn't say physics lost, but he says mathematics grew gloriously in the last 20 years, which means physics lost. Okay. Now, whenever there is a divorce, there is a bounce back. Okay. And it is on that bounce back that mathematics found the partner in engineering sciences. Okay. And what started this bounce back marital affair between mathematics and engineering, this was catalyzed by a very famous communication engineer, Claude Shannon. I think Claude Shannon has not got the type of recognition that he should have got. He should have got much more than what he has got. He was at the Bell Labs. He wrote a master's thesis at the age of 21, which is considered as one of the most important master's theses ever written. So he essentially made a science out of the art of digital design. Okay, but more importantly, he wrote a very seminal paper in 1948, the mathematical theory of communication. Okay, this is, I think, one of the probably greatest papers ever written in the history of science and engineering. Okay, it runs into several pages. Okay, so 379 to 423 and 623 to 3. And essentially, we are living in the world today because of Shannon. The digital world that we are living in is because of Claude Shannon. Okay, the two important ideas we introduced in his paper were the idea of entropy, the information content, and the entropy. Okay, in the context of information, and the idea of the capacity of a channel in the context of the bandwidth and the signal to noise ratio. Okay, the more signal and less noise, better data can be transmitted. Dr. Unikrishnan was telling in the afternoon about Paul Raj and others how they are struggling with the sonar business, where there was more noise than sound. How to filter out that noise and extract that sound is a big problem. Okay, so but anyway, not only Shannon has also shown a limitation. What is the maximum capacity? What is the maximum that you could transmit? Also a limit. Of course, it's very difficult to achieve that Shannon limit. But he said there is a limit to what you do. It is like you are in Bangalore, you always talk about traffic jams. The broader the road, the better the bandwidth be. And less noise, that is no signal lights, no bumps, no potholes, no donkeys or monkeys or on the road, or auto rickshaw fellow going this way and that way, then less noise, more traffic. That's essentially the common sense idea that Shannon brought about in communication. But more than this, I feel that the importance of these two equations are in the fact that whatever important equations, mathematical equations that were written up to Shannon's time, like Maxwell's equation or the Navier-Stokes equation, okay, or E equal to mc squared, all these equations were in the context of a natural phenomenon. Shannon, for the first time, wrote two equations not about a natural phenomenon, but about an engineering system. A system which you build, you operate, you control. And there began the marriage of mathematics with engineering, with Shannon's work, bringing in that analogous to the physical sciences, we could also in engineering sciences write appropriate mathematical equations, manipulate with them, handle them, and develop theories and technologies. Okay. Well, I'll just show this. The professor at Cambridge works on neural networks, and according, he says that one of the greatest intellectuals of all times, Shannon, both Aristotelian and Platonian combined together, he had is a tremendous knack, a cunning intelligence to develop these theories. So remember that Stewart said Maxwell's equation that didn't change the world, they just opened up a new one. We could say the Shannon's thesis and equation didn't change the world, they opened a new one, and that's the one we are living in, the digital world. Okay, so we had Wigner. We talked about the unreasonable effectiveness of mathematics in the natural sciences. Then Dyson, who said, well, that ended in a divorce. Then Shannon had started the marriage, and the marriage was confirmed by a third talk, or a third speech, or a third essay by a famous communication engineer by name Richard Hamming, who was also at the Bell Labs. And his title, The Unreasonable Effectiveness of Mathematics. Wigner, Unreasonable Effectiveness of Mathematics in the Natural Sciences. Divorce has taken place. Natural sciences are gone. So it is only the unreasonable effectiveness of mathematics. And Richard Hamming starts his article by saying, well, Wigner talked about the effect of mathematics, unreasonable effects of mathematics in the natural sciences. I am not going to talk. I am going to talk about the unreasonable effectiveness of mathematics in the engineering sciences, and particularly the unreasonable way mathematics has come to my rescue in my work. And he illustrates several instances of his work, from communication engineering to rocket science and whatnot, when he was working at Bell Labs, how mathematics has come in a very unexpected manner to his rescue. So Richard Hamming's article is a confirmation of the fact that mathematics has diverse physical sciences, has married engineering sciences. These three articles, in my opinion, are very important to keep track of the history of the changes of applied mathematics. One is Wigner's, then Dyson's, and the third one is Hamming's. Okay. These tell you what has happened in the flow, in the change that has taken place in applied mathematics. Okay. So this is the starting point of the the marriage of mathematics with engineering. Up to the second half of the 20th century, there was up to the Second World War, I suppose, the mathematics, the interaction between mathematics and physical sciences was just phenomenal. But however, something happened somewhere. Shannon pulled mathematics, the physical scientists somehow, the natural scientists somehow were moving away from mathematicians. Maybe mathematicians are also responsible for that. And somehow Shannon's work pulled the applied mathematicians towards engineering sciences. And all the technologies that we have seen that have come in the last 70 years is all mathematics, has an undercurrent of mathematics. Whether you have a mobile phone or the photos that you take with the mobile phone or the manner in which you transmit money from one bank to another bank, whatever we do, everything is, there is an undercurrent of mathematics because of the interaction of mathematics with the engineering sciences. Okay, so what I want to do in the next few minutes is point out a few things of such unreasonable, very quickly, how unreasonably mathematics has got into the engineering sciences over the last 6 to 7 decades. Okay. And of course, whenever one talks about such things, there are limitations. One is the limitations of the speaker's knowledge. Okay. I am not an engineer. Okay, all these technologies have happened when I've become old. I was born at that time when I had no electricity in my village. So the only time I saw electricity was when I came to join college in Bangalore. Until school, we didn't have electricity. And we used to ride on a cycle 3 kilometers away to the government hospital where the doctor had a radio. And there we would go and listen to the cricket commentary. Okay, so now today you just click cricket info or cricket next and see what's the score from your mobile. So that is the change. Even as far back as just 1980s, I wanted to make a call to the US. I didn't have a phone in my house. I had to go all the way from the North Bangalore to South Bangalore to one of my relatives' house who had a phone, book a call, sleep there in the night until I got the connection, and then spoke. Okay, that was the technology. But now everything has changed. All that is because of this. Okay, so a talk like this has to be, first of all, the limitations of the speaker's knowledge. Secondly, the bias that the speaker has about certain areas, and his experience with these areas. So therefore, whatever I am going to say is more illustrative in nature than exhaustive in nature. Okay, and I have had the fortune of interacting with some very clever, good students at IISc, learn a lot from them, and particularly a lot of engineering students, electrical sciences. There is one, Unikrishnan is there. There were electrical communication engineering, electrical engineering, electronic systems engineering, and similarly from the mechanical sciences, aerospace, mechanical and civil and hydraulic engineering fellows. I had a fortune of, I had even worked in the civil engineering department for 4 years. So I had the fortune of interacting with them and learning from them a lot. Okay, and particularly after my retirement, I completely was with the electronic systems group. So I had the great fortune of even entering into the labs sometimes and is asking them, what is this doing? Why can't you do it this way? And exhibit my ignorance also sometimes. So that so therefore my bias, my lack of my knowledge, and whatever little exposure I've had, all these will be built into these deficiencies of this talk. Okay, but at the same time, I am going to talk about only elementary areas, subjects in math which are common, and just point out where they have played that role. Okay. Okay, the first one is, of course, linear algebra. Do I have it in the wrong side? Yes. This is backwards. Okay, the first topic that I would look at is linear algebra, which perhaps everybody now learns. Okay, and I think one of the greatest proponents and man who pushed it was Gilbert Strang. Goes on talking everywhere that people should learn linear algebra and so on. Okay, so look at this is what. This is the copy I have, the 2007 one, but there is a later version of this handbook of linear algebra. But here the author, the editor, Leslie Hogbin from Iowa State University, very politely says, now look here, this now, it's very important for computer scientists, engineers, social sciences, etc., etc. So it's a very important subject, and rather very politely. But now, Gilbert Strang is very aggressive. I personally believe that many people need linear algebra than calculus. Richard Feynman is gone, okay? Better learn linear algebra. And Eisenhuth may not agree, but he is not teaching mathematics in the 21st century, and maybe he wasn't a great teacher, but we'll give him the benefit of doubt. Certainly, the laws of physics are well explained by differential equation. Newton needed calculus, fine. But now things have changed. Life is a little more difficult, and everybody has to learn linear algebra. More universities are still struggling to come up to terms with this fact that to change the curriculum and bring it to this. And so he explains how linearization helps and how when the number of variables is very large and you have to deal with huge matrices like in finite element method, if you are studying arrow structures, you may be talking about a matrix which is 1 lakh rows and 1 lakh columns. I mean, they are talking about such huge computations. So therefore, he says in such cases, your knowledge of linear algebra will come into effect. So therefore, according to Gilbert Strang, linear algebra should be the first course that everybody should learn. Okay, not because I taught linear algebra, but I think that's the easiest to teach also, which you don't really need too much effort, so you can slowly handhold the student, walk with him for a while and leave him. Okay, and if he's clever enough, notes some computations also, manipulates with them, and then really nice. And some of my students could do even nice geometrical things on this screen and show me, sir, this is what you are talking about. They come and tell me, because they are good in computer programming and all, they could get the visualizations, which I cannot. Because, of course, I had a tabletop I got finally in my office 2 years before I retired. Okay, so we hardly had, the best thing we had was the IBM 360 computer, which was housed in a huge, big building in the institute, and we had to punch very painfully several cards and put rubber band with them and then put it in the computer center and wait for them to give you a preprint. And some naughty fellow will go and remove one card from your bunch and the whole program is collapsed. Okay. But now, of course, you can do many of these things in your laptop. Okay. So what is the central problems, simple central problems in linear algebra? System of equations. This is how the whole subject started. Just to show that where the unreasonableness has come up to. Okay. We started with simple equations right from the old Chinese manuscripts and so on. One can find problems stated like 1 goat cost, 10 goats and 14 cows cost this much, and 18 goats and 14 cows cost this much. What is the cost of a goat and what is the cost of it? Okay, this is, I had a maths teacher. He would always come to the class and say, 4 dosas and 3 vadas cost this much. 8 dosas and 5 vadas cost this much. What is the cost of a dosa and a vada? That was more interesting problem to us than 8 cows and this thing. So there was, these sort of problems are very common, which start in high school, we call method of elimination or whatever it is. And so this is the starting, very humble beginning for this subject. So what are the main questions? First of all, as a mathematician, do we have a solution? The answers can be yes or no. Now, if it is yes, okay, fine. If it is no, what do we do? We say, stupid fellow, you gave a problem which has no solution. Or we go further and see what best we can do, and we get something called the least square solution. The error, least square error. The solution that, something that gets closest to what you wanted, but you could not get, but you get somewhere there, okay? So roughly this is what technique to solve means. Again, if the solution exists, how many? 1, infinity. If it is 1, find it. If it is infinity, go and find all. Okay, these sort of questions will keep coming. These are the basic elementary questions that one asks, and the sophistication begins. These were all put in the language of the matrices. So what were the nice things that you see was the separation of variables. You separate all the variables, one equation for each one unknown. So basically it's a diagonalization of the coefficient matrix. And if you cannot do it, at least do triangularization. And then when you do the diagonalization, do it cleverly so that computations become easy. So you can do similarity, orthogonal, or double orthogonal. Which one is possible in each case? Of course, the last one, the double orthogonal, is the one that is widely used today. It's called the singular value decomposition. Okay. And of course, for a mathematician and a differential equation person, in the triangularization formulation, it is the Jordan canonical form. That's because you can generate from that. That is possible for every matrix, whereas that is left side is not always possible. Left side only the last one, the double orthogonal SVD is possible for all matrices and for all rectangular matrices also. Whereas triangularization is always possible, and that helps you in the function theory also. It gives you computational methods for finding functions of a matrix, and therefore it comes handy in dealing with systems of differential equations. Okay. Okay, and then people start develop the various basic ingredients for this. The ideas of elementary row reduction, Gaussian elimination, iterative method, eigenvalues, eigenvectors, etc. That thing, no engineering was there. Okay, this was all purely from a mathematical point of view. There is an equation I want to solve, a system, system of equation I want to solve. How do I solve? What is the best way of doing it? And maybe until for a long time, it was only maximum they could deal with was a 3 by 3 matrix, okay? Because computation by hand. So where was the early motivation? The early motivation, one was geometry, quadratic forms, or classification of curves, second order curves, third order surfaces, or three-dimensional surfaces. How do you classify an ellipse, a parabola, or hyperbola? And then similarly, all the three-dimensional surfaces, hyperboloid, paraboloid, and so on and so forth. I think they don't teach that at all these days, the three-dimensional geometry. We had a beautiful course in my MSc from one book by Bell, R.T. Bell or something like that. Very wonderful 3D geometry. Okay, 3D solid geometry. Okay. Anyway, it's all about this. Again, this was started slowly coming into physics now. Because Euler and Lagrange and others were involved. So classical mechanics, small oscillations about an equilibrium. So the kinetic energy was written as a quadratic form, and the diagonalization of that told you the frequencies of normal modes of vibrations, and the eigenvectors showed the directions in which the small oscillations are taking place. And then, of course, general differential equations. Slowly, it went on to partial differential equation and their classification. Now, what has happened recently? Professor Joshi is looking at his watch. Okay, he still not warned me. Okay. Uh, so, so I will now quickly go through it. Because of the power of computation now, we have moved from the huge building for the IBM 360 to a small corner. You keep a server and you connect your server from your home and you can do anything you want. Okay, such powerful computational facilities are there. Therefore, people use it in image compression, signal processing, search engines like Google, or latent semantic analysis, or hypertext induced textual search, and so on and so forth. I think it's just unbelievable. These were all not thought of when linear algebra started. And this is what is the unreasonable effect. See, 50 years back, 60 years back, when, let me tell you correctly, 62 years back when I was doing MSc, nobody even talked about these things. Linear algebra, only linear independence, solving systems of equations, and diagonalization, quadratic forms. There it ended. But now, all that's gone. More important thing is, how do you compress images using this thing? How do you do signal processing? How do you do the discrete Fourier transform? And so on and so forth. And then so the digital signal processing. And then, of course, Google is one of the greatest examples of how this is used. And the aerospace fellows, through their finite element method, show you how large structures can be done. And data mining fellows, of course, they use it. So this is the unreasonable way in which the marriage has produced tremendous effects in engineering. Okay, so these are all children born out of the marriage of mathematics with engineering. Okay. Of course, now everybody talks about learning models. I don't understand a word of what they talk about, but I don't know who is learning what. Okay, but they talk about learning models. Okay, because by the time these people joined the institute, I had stopped going to the institute, so I don't meet them. Well, so therefore, if Hermann Wouk were to meet Gilbert Strange today, instead of Richard Feynman, he would say, better learn linear algebra because that's the word God talks, or that's the language engineers speak. How much time I have? 15 minutes? No, tell me. Yeah. Okay, next is the next important area is Fourier analysis, which I found with my interaction with all these engineers here. See, it's a very, I was surprised that about 4 or 5 years back, some 3 people from General GE, Bangalore, came to my office. I still had an office at that time in IISc, and said, sir, can you come and teach our engineers Fourier series and Fourier transforms? This is so important for us in signal processing. Many of them don't seem to have a clear understanding of it. So I was surprised that these big corporate fellows want to learn Fourier analysis. Finally, at last, they want to learn Fourier analysis. So that, in my opinion, is another important branch of analysis, which has become, but at the end, I will tell you for 2 minutes about it. Fourier analysis, which started at something about in 1807 with Fourier's memoir on heat conduction equation, which he submitted to the French Academy and was awarded the prize. Of course, a lot of controversy was criticized heavily by Laplace, Legendre, and other Poisson for a lack of mathematical rigor, but still they gave him the prize for the idea. That the idea that he had was something original and beautiful, and therefore they gave him the prize. So it involved, basically it all started with solution of a partial differential equation, and not even wave equation. Because everybody says, oh, you are decomposing everything into sine wave and cosine wave. No. Heat, there is no wave equation. Heat equation was not the wave equation. It's a parabolic differential equation. It's a diffusion equation. So for some reason, I mean, there is a reason, but I will not get into that. He was motivated to go into the sine and cosine waves. And so it was a problem purely on conduction of heat in solids. And this was a parabolic differential equation. In the beginning came Fourier series, therefore. That was about 210 years ago, 215 years ago. Fourier series started, and it was mainly dealt with periodic functions. And the engineering effect started coming with time invariant systems, linear time invariant systems, which I will not get into. Basically, it is an input-output system which is which commutes with delays. Okay, that's all. Basically, put that if you have a system and a delay, you interchange their position. First delay and system, the effect is going to be the same. That's what the linear time invariant system. This was the first real breakthrough, and there is a linear algebra in this. It came so efficient in handling linear time invariant system because the idea of diagonalization came into this. The sine and cosine functions turn out to be the eigenfunctions for this system, and the corresponding eigenvalues had their own meaning. Okay, the Fourier coefficients were the corresponding eigenvalues. Okay, but anyway, as connection with the eigenvalues. So that was the first entry in the electrical engineering. The linear time invariant system slowly made its way. Fourier series made its way into engineering. Then came Fourier transform, analogously for non-periodic functions. Okay, and that looked about linear time invariant systems where the input-output functions were non-periodic, whereas in the original first linear time invariant system that studied where the inputs and outputs were all periodic functions. Then they generalized it to non-periodic functions, and there was a beautiful marriage. Anyway, the LT, both of them diagonalize the linear time invariant. That is the main idea of why they work. Why it worked was the diagonalization idea at work. The eigenvalues were the sine and cosine function in both, and in that case, the Fourier coefficients were the eigenvalues. In this case, the Fourier transform were the eigenvalues. Then the next move to the unreasonable effects, from the LTI to the more unreasonable effect. We have Fourier series on the one hand, and we had the Fourier transform on the other hand. There was a marriage between the two. And what came out of that was the sampling theorem. There was an interaction between the Fourier series and the Fourier transform, and we got the sampling theorem, which started all the signal processing, etc., how it should be done and all. And it was catalyzed by the discrete Fourier transform. And in the 60s, 1960s, came the fast Fourier transform algorithm, and all of them put together, the digital signal processing was born. So you see, 1807 was what Fourier series started, and immediately following him came the Fourier transforms actually. But 150 years later, they were the right tools that were needed to do signal processing. That is what is called the unreasonable effectiveness, according to Wigner. And now that is another outcome of the marriage of mathematics with engineering. Of course, when I say signal processing, the word signal is used in a very general sense. Okay, it's not only sounds or image signal. So I use the word, it could be one-dimensional signal, time varying, or two-dimensional signals, or three-dimensional signals like holograms, etc. Okay, or even much more general, like it can be speech signal, it can be audio signal, it can be in mechanical problem, it can be velocity, it can be fluid mechanics problem. Even when you start your automobile car, the bonnet gets heated, that's a signal. That is also a signal. Okay. So the word signal is used in a very general sense, and there can be all the processing is done using Fourier analysis. Okay. Now people went further. Now things moved further now in Fourier analysis. Okay. Now we'll conclude with Fourier analysis itself. I will not go into the other problems. The problems were, you want to analyze the signal locally or globally. If you look at Taylor series and Maclaurin series, you are using derivatives. Derivatives are local. We look at what is happening, h going to 0, closer. But if you look at Fourier series, you integrate from 0 to 2 pi. You take all the values. It's global. Okay. So these are all global analysis. This is local and that's global, but this is not suitable for global and that is not suitable for local. That's where the problem is. And can we do both simultaneously, local analysis and global analysis? Then first thing came windowed Fourier transform by Gabor. But these were rigid windows. You could not adjust the width, fixed, and then move them and see the signal. Okay. Now, therefore, the question is, can we get flexible windows? And then were born the idea of wavelets. Okay. So that originally it was a mathematical problem in the context of interpolation. You see, again, it had nothing to do with all the signal processing or anything like that. It was already there, but they were not smooth, and therefore a lot of work was done. I'll go back to this. Then it came to image processing and signal processing. A lot of the JPEG 2000 protocol has the wavelet protocol built into it. Okay. So the importance of the recognition of the fact that eventually this wavelet analysis is a very important branch of engineering and applied mathematics was confirmed by the award of the Carl Friedrich Prize for Applied Mathematics in 2010 in the ICM in Hyderabad to Ois Meyer for his mathematical theory of Fourier. And Ingrid Dobschi being elected as the president of the IMU in recognition for her work on wavelet theory. So that's one of the big things in signal processing and particularly image processing. And of course, this leads to the very general problem of basis. Now, because I don't have time, I will not go into slides. I will talk generally and close. Okay, but today, therefore, if Herman Wouk has to goes to EPFL and meets Martin Vetterli, he will tell him, you better learn Fourier analysis. That's the language that engineers speak. Okay. Maybe I will, of course, another area which had started as a simple problem in calculus of finding maxima and minima in order to decide the shape of a curve. It has eventually grown into a major problem in engineering. So I will simply skip that. Okay, now today we have what are known, first initially we had least square and then linear optimization. Okay, that grew into several areas. Then we had today the most important area of optimization is convex optimization, and a very important method is called interior point method, and it has its various applications. I think unbelievable. And of course, finally I will add machine learning. See, these days better to add machine learning to everything. Okay, that's the craze. Okay. So it's probably one of the bread and butter issues for engineers, optimization. Okay, but it started off as a very elementary, simple problem in calculus of deciding how the curve reaches its maximum, minimum, so that we can sketch the curve, see the shape of a graph of a function. Okay, so therefore, if he goes to Stanford and meets Stephen Boyd today, he will say, you better learn optimization. Okay, that's the language. And I'm not going to even open this slide. Probably one area which nobody expected, even Hilbert did not expect in his famous lecture in 1900, that probability theory is going to make such a tremendous impact as an applied mathematics problem. Okay, applied mathematics tool. I think maybe again, as I said in the beginning, because of Shannon, he showed how simple ideas of probability tells you about the entropy of an information and all that. People start. Of course, why should an engineer be interested in probability theory? Because he says we work, they use instruments, they make measurements, there is always certain uncertainty in it. There is noise, the disturbance, that's called noise. So you have to model the uncertainty, the components of the instruments, the quality of the components, the conditions under which they operate. Everything has a certain amount of uncertainty that is built into it. So we have to model uncertainty, and who else can do it for us than probability? And therefore, random processes, studying random processes has become, the impact of random processes has been phenomenal in the last 30 years to 40 years. I was surprised that things like Markov chains, hidden Markov models, all these are used in speech processing and other areas. And I think maybe this is one area which nobody expected that God would speak. Okay, and Einstein said God never tosses a coin. Okay, he doesn't play dice. Okay, but it looks like engineer believe in it. Okay, that okay. So let me just go to the conclusion straight in order to. A lot of things are there. This also I kept. Finite element methods, I don't want to tell, that's another important area. And then the next important one is, of course, the ultimate application of number theory, which is perhaps nobody expected in cryptography today. I think it's probably the bread and butter. I think that is the sort of, what is it, the golden child of this marriage between mathematics and engineering, is application of number theory. So let me go to the conclusions, therefore. Okay, there you are. So this also, I will not bother about these things. There is no time. Okay. So RD said there is a very high degree of unexpectedness combined with inevitability and economy. And this is what has happened with all the applications of mathematics and the engineering sciences. One is the unexpectedness, and then the economic way of solving their problems. Okay. And here is Hertz. I think I like this quotation very, very nicely. This really tells you about the unexpectedness. The equations are wiser than we are wise. Even they are wiser than even their discoverers, that we get more out of them than was originally thought about. That, I think, is what is the most unexpected nature of mathematics. Okay, the equations give us more back than what we originally put into it. And so we were talking about an article of faith. Okay, here is an article of there is a famous book, there is a nice book called It Must Be Beautiful. Okay, in that there is a quotation which says, for any phenomenon that we want to study, there must exist a set of fundamental mathematical equations that describes it. Or if there is none, someday somebody will discover it. Okay, but probably, okay, for every faith, there must be an alternate faith. Okay, somebody will question it. Okay, and Feynman is always there to question it. Okay, Feynman said, what is the guarantee that somebody someday will say, mathematics is not the right way to write all these things. There is a better way of doing these things. Okay, But until such time, there does not seem to be any escape from the impact of mathematics on the engineering sciences. And Ulam would say, do not lose your faith. A mighty fortress is our mathematics. Mathematics will rise to the challenge, as it always has. So as mathematicians, have faith in your subject. As engineers, have faith in mathematics and learn mathematics. And mathematicians, listen to engineers. They have a lot of problems which, so in a marriage, Vijay, he asked me, you asked me, right? Who is the husband and who is the wife? You. Well, it doesn't matter who is the husband and who is the wife. The husband better listen to the wife and the wife better listen to the husband. So mathematics better listen to engineering and engineering better listens to math. Then there will be a good family. Okay. So with that, I'll conclude. Thank you very much.
Questions, comments? There is so much, of course, that he has covered that it may be difficult for you to focus them, but that's okay. I mean, you can ask on any aspect he has covered, or even something new if you like, which is related to what he said. Feel free. You want to say something? You want to say something?
Professor Vittalavu, it is very interesting to hear you. Okay, I'm here.
Yeah.
I'm here. I'm here.
Yeah, okay.
What I wanted to place before you is all your talk said mathematics has asked several occasions, engineers, you learn this, you learn this, you learn this. So what type of mathematics, for example, in linear algebra, what new problems, new tools you would like to get in order that the new challenges are answered? Do you have, what I mean is, do you have some idea of, at least in linear algebra, what are going to be the new developments in theoretically linear algebra, so that you will be more efficient in having answers?
So your question is, what new things should be discovered in linear algebra, therefore they will become applicable? Is that your question?
Yeah. Is there any such thing, thought going on?
Now, I think as far as linear algebra is concerned, theory part I think is fairly completely developed. Okay, I think it's one of the full neatly developed subjects is linear algebra. And I say completely, fully, neatly developed, finite dimensional. The infinite dimensional linear algebra still has a lot of questions. Okay, and the infinite dimensional linear algebra, when you are dealing with signals as functions, you will have to deal with infinite dimensional linear algebra of functions, but then you will have to bring it down somehow to finite level to compute. Finally, you will bring it, if you want to compute, you are going to bring it everything to finite level. What is the best way to do it? See, for example, finally, the question is, for each problem, eventually, the signal, depending on the signal, there must be a right basis by which I can study such signals. What is the right basis for the right problem? You may say, I will say 1000, 0100, but that's not the right basis. Most of the problems, it's a useless basis. So you go to eigenbasis. So therefore, for each problem, each signal space, there must be a right basis. What do you mean by right basis? Today, we want to compute everything. What is the efficient way of doing linear algebra from the computational point of view? What is the most efficient way of doing linear algebra? Maybe, even multiplication is a very fundamental question. How do you multiply two matrices efficiently? You see, these are the questions. But at the end of the day, I would say To quote John Kennedy, ask not what linear algebra can do for you. Ask what you can do with linear algebra.
Any other questions or comments? Any other questions?
This talk I see as marriage between mathematics and circuit branch engineers. Like E engineers, EC engineers, and IT computer science. How do you conduct a marriage between engineers and other engineers and mathematics? So what are the subjects? Main
No,
subjects?
I mean, as I said, what I said was illustrative, not exhaustive. If I were exhaustive, I would have told you how we have got into computer science, how it has gone into information technology, everywhere. I only said illustrative. Even in illustrative, I could get through only 2. Okay, so it is everywhere. Mathematics is, my philosophy is the following. Whatever you see in nature, how do you see? I mean, I cannot say how you see that bottle. Are you seeing the bottle the same way I see? It depends on how your mind perceives. So finally, you see nature or anything in your mind. And mathematics is done in your mind. Somewhere they will have to interact. And eventually the marriage will take place.
Finite element techniques, for example, it involves linear algebra, isn't it? Finite element techniques. Finite element techniques.
I think too much feedback. Finite element method. Linear algebra. See, finally, when you come down to computation, everything is brought down to finite dimensional. You do matrix computation. I mean, you can't get away with it.
Civil engineering and whatnot.
I did not do optimization. That is there in every branch. I just showed. Finite element method, mechanical, aerospace, civil sectors, everything it is there. Probability theory. If you want to design a building to take care of earthquakes, there is uncertainty. Modeling should be done using probability theory. So there is no end to it. Everywhere it is there. Okay.
So today, Professor Joshi was mentioning asymptotic analysis. So similarly, there is asymptotic linear algebra of very large matrices, which you can't handle within the conventional.
Now you should do linear algebra from the computation point.
Yeah. I mean, it's called the asymptotic linear algebra. That's very.
Yeah. That's the main thing.
Also, I just wanted to ask you, there is a development of non-commutative mathematics. Non-commutative geometry is there, non-commutative set theory is there.
I think you keep your mic a little far. There's too much of feedback. Non-commutative mathematics. I have no idea about it. I have absolutely no idea of even about non-commutative algebra, to be honest. I have no idea about it. I don't know. Uncertainty principle. It's everywhere there again. In Fourier transforms, it is there. I don't know. I know uncertainty principle exists in Fourier transforms. In almost every transform, it will exist, the sort of uncertainty principle. And beyond that, I don't know anything about uncertainty. Uncertainty principle to me is what we are doing in all our entrance examinations. If you try to quantify quality, you are going to mess up. Okay, that is uncertainty principle for me. Yeah. Okay.
And to answer Dr. Murugan's question, what he has done was serving a buffet lunch. Whichever food you like, you eat. It's not a fixed lunch. So for your choice, you can have some other items in the menu, and then you also have buffet lunch. In the morning, I described Professor Vittal Rao as a very inspiring teacher. Now you don't require a proof. So I will request, I'm sure that nobody slept. Though Vinod gave us a very good lunch, nobody slept at between, say, 2:45 and 3:30 and so on. So I will request all participants have a big hand to Professor Vittal Rao.
Thank you.
Any other questions before we close? Yes, you have something to ask? Anybody at the back? Backbenchers, as they say, or back chairers? Well, okay, let me perhaps then conclude. Of course, I want to thank Professor Vittal Rao, but there was a certain prophecy in what he said, because I also came to think along those lines for a very different reason. I'll tell you what it is. When we were in IIT, I have taught in IIT for many years. And in IITs, there is a standard pattern for engineering mathematics courses. It begins with Calculus 1, Calculus 2. So in Calculus 1, all these mean value theorems and that kind of thing. In Calculus 2, then differential equations, whatever. And after those courses are over, then there is a linear algebra course. So that went on, and we all thought it is fine, why change it? But then after retirement, I came to this COEP, College of Engineering, Pune, and there I found that the very first course was on linear algebra, not calculus, that is the standard practice. Then I inquired, why do you start with linear algebra? Then they said that reason, I could not have guessed that reason. In IIT, what happens is, there is the examination. May I proceed? Okay. There is the examination, JEE, of course, and either you get in or you don't get in, and depending upon your rank, you are given a choice, and then everything is settled before the classes start. Now, in engineering colleges, that is not the case. The major admissions are done at the beginning, but then there is secondary, tertiary batch, which joins later on. So the logic was that after the classes started, say 2 weeks later, some new batch comes, but in the same course, not the next year's batch. Then mathematics is a growing subject. So how will they make up? And then another batch might come. So the logic was that if you start with something difficult like mean value theorems where completeness is needed, it will be very difficult for the latecomers to join it and to assimilate it. On the other hand, if you start with linear algebra, especially matrices, determinants, etc., either some students are familiar or they can easily pick it up. So it was more a practical convenience. And that's how the courses in these state colleges, engineering colleges, were framed. Then while teaching, I realized that by accident, that was a better arrangement. Because, as was said by Professor Vittal Rao, in calculus, what do? What is a first order approximation or linear approximation? That is derivatives. So many things of calculus, if you interpret in linear algebra term, they look very natural. What is the divergence of a vector field? That delta u by delta x plus delta v by. Now, these are the diagonal entries of the derivative matrix. So it is nothing but the trace of the derivative matrix. And once you realize this, then invariance of the divergence, that is a trivial corollary of invariance of trace. But people don't seem to realize this. So by accident, I came to know that yes, that is a right arrangement. First linear algebra, then calculus. And use linear algebra as a tool for calculus. So as a result, now you might say the purpose was to advertise my book, but finally it led me to write a book. That book has come out only a year ago. That book is called Multivariate Calculus Through Linear Algebra. There are two parts to it. First is purely linear algebra. The second is calculus, but using linear algebra. Okay, so Now I can say that somebody has already said this. This is not some new discovery. But yes, linear algebra should come first, and then things will come. Many things will come. So as you said, if von Neumann, not von Neumann, but Feynman, he was alive today, he would say, hey, wait a minute. First, have you studied calculus? Instead of that, today the right question will be, have you studied linear algebra? If not, then first you study that. Then you can talk about calculus. Okay. But these are parts of mathematics. So just because calculus is replaced by mathematics, it doesn't mean a divorce between engineering and mathematics. They are also part of mathematics. So this happy ending of that marriage, and also the happy ending of this conference now, because this is the last talk. But anyway, the good news is that his plane is delayed. So he will still be available. So if you have any questions or comments, please feel free to discuss them over a cup of tea.
See, I had worked in REC Calicut. Don't feel bad about it. There are two types of engineering teachers. One who accept that mathematics is needed, and the other group who say that mathematics is not needed. So what I would request Vinod is to convene a seminar of this type and invite Professor Vittal Rao as one of the speakers. He will convince this. Let me take 1 minute more. When I applied at Cochin University, I was working in REC Calicut. There is one Professor KBN Nambudiripat who gave us lectures every week on applications of mathematics. He's a mechanical engineering faculty member. So when you may know KBM. So when I applied for a Cochin University job, the expert also was from IIT Chennai, and he asked me, what mathematics do you know? Then I told that I'm working in REC Calicut. Oh, you are working in engineering college. So I will not disturb with topology or something like that. I will ask questions on differential equations. The unfortunate part is that I don't know any differential equations, though I have taught. So just 1 week before the interview, Professor KBM gave a talk in our department and explained the application of second order differential equation, free oscillation and forced oscillation. And what he did was he hit the board table. Okay. Now in the interview board, I think Professor Das, he's no more. He asked me, do you know some applications of differential equations? You know what happened to me? The hitting of by Professor Nambudripad on the table gave me some hint. Then I said, yes, I know about free oscillation and forced oscillation. Professor Das did not ask any further question, so I was selected. So this is what, what happens in engineering college. This is true for RSCT also. Those who like mathematics, engineers, and those who don't like mathematics. So what I would request is educate those people who don't like mathematics. That is your task. Okay. And invite Professor Vittal Rao. That's it.
May I request KD Joshi sir to please hand over a memento to Professor R. Vittal Rao sir. Thank you, KD Joshi sir, for chairing the session. Now we will have the tea break. Tea will be served outside the seminar hall.
So this was the final session of the conference. With this, we conclude the conference. I thank all the resource persons, delegates, management of the institution, principal, all my colleagues, non-teaching staff, technical staff, all the participants who participated in this conference. Thank you very much.
many of these products, finally, there is some calculation or commutative rates. Because grids, then they recognize two rates. But what it is, if you don't have a commutative rate, how will it